Hello and welcome to this 16th set of problems on complex numbers. In this set, we will solve problem number 151 to 116. So as I always say, I'll say this again that when I'm reading the problem, you should pause the video and try to solve the problem yourself. If you cannot solve the problem yourself, then look at the solution. So without further ado, let's get started. Problem 151 says that consider an equilateral triangle A 2 by square root of 3 e to the power I pi by 2, B 2 by square root of 3 e to the power minus I pi by 6, and C 2 by square root of 3 e to the power minus I 5 pi by 6. If Pz is any point on the in circle, then find the value of AP square plus BP square plus CP square. So we find the complex numbers. We take the Euler's form and convert it into Cartesian coordinates. So A becomes 2i by square root of 3, B becomes 1 minus I by square root of 3, and C becomes minus 1 minus I by square root of 3. So clearly, if you see the points A, B, and C, then the modulus is 2 by square root of 3. That means they will lie on the circumcircle with the radius 2 by square root of 3. And this triangle is equilateral, so its centroid will coincide with circumcenter. Hence, we can say that Z1 plus Z2 plus Z3 is equal to 0, and Z1 bar plus Z2 bar plus Z3 bar is equal to 0. Now, clearly you can find that the radius of encircle is 1 by square root of 3. So any point on the encircle would be 1 by square root of 3 cos alpha plus I sin alpha. Okay, so we have this circumcircle with radius 2 by square root of 3, and we have the encircle with radius 1 by square root of 3. Now AP would be Z minus Z1 mod square, which will be equal to mod Z square plus mod Z1 square minus Z Z1 bar plus Z bar Z1. So similarly, we can find BP square and CP square. So the sum would be 3 mod Z square plus Z1 square mod Z1 square plus mod Z2 square plus mod Z3 square minus Z into Z1 bar plus Z2 bar plus Z3 bar minus Z bar Z1 plus Z2 plus Z3. Now this and this will be 0, and the radius of encircle, that is mod Z, would be 1 by 3, 1 squared, and Z1 whole square, Z1 bar, mod square plus Z2 mod square plus Z3 mod square would be 4 by 3. So 4 by 3 twice, and so the total sum is 5. Problem 152 says that if A1, A2 up to An be the vertices of a regular polygon of n sides in a circle of unit radius, and A is equal to A1, A2 mod square plus A1, A3 mod square plus up to A1, An mod square, B is equal to A1, A2 mod into mod of A1, A3 up to mod of A1, An, then find A by B. So we let O to be the center of the polygon, and Z0, Z1, Zn minus 1 represent the vertices A1 up to An. So Z0 would be 1, Z1 would be alpha, Z2 would be alpha square, and Zn minus 1 would be alpha n minus 1, where alpha would be e to the power I2 pi by n. That is the angle between two vertices of the polygon. So A1, A2 mod square would be alpha r minus 1 mod square. That is, we exchange the term, it would be mod of 1 minus alpha r square. That is 1 minus cos 2r pi by n plus I sin 2r pi by n mod square, which is equal to 1 minus cos 2r pi by n whole square plus sin square 2r pi by n. That is 2 minus 2 cos 2r pi by n. So we take the sum from r is equal to n, we get the sum as 2n minus 4 here. Okay. Now what we do is we try to find out B, which is equal to mod of 1 minus alpha, 1 minus alpha square, 1 minus alpha to the power n minus 1. Okay, so we need to consider this once. All right. So here, when we take the sum, it should not be 2n minus 4. It should be 2n. Okay. Yes. 2n minus 2 into real part of this. Okay. So real part would be 0. Okay. Because 1 plus alpha square plus alpha to the power n minus 1 is equal to 0. So then this whole would be minus 1. So minus 1 into minus 2, it is 2n. Sorry, I missed that. Now we try to find b. So b is 1 minus alpha into 1 minus alpha square up to 1 minus alpha to the power n minus 1 and modulus of that. Now these are roots of z to the power n minus 1. So z minus 1 into z minus alpha up to z minus alpha to the power n minus 1 is equal to z n minus 1. So z minus alpha square, z minus alpha to the power n is equal to z to the power n minus 1 by z minus 1, which is equal to 1 plus z square up to z to the power n minus 1. So we substitute z is equal to 1, we get the whole thing as n, which is b. So a by b is equal to 2n by n, that is 2. Problem 153 says that if 1 plus ix by a multiplied with 1 plus ix by b plus multiplied with 1 plus ix by c and so on is equal to a plus ib, then prove that 1 plus x square by a square into 1 plus x square by b square into 1 plus x square by c square and so on is equal to a square plus b square. This is very simple. We take left hand side as z1 and right hand side as z2. So since z1 is equal to z2, z1 bar is equal to z2 bar. So z1 bar is equal to z2 bar, that is z1 square is equal to z2 square. So we can say that 1 plus x square by a square into 1 plus x square by b square into 1 plus x square by c square is equal to a square plus b square. It is the same thing as taking modulus and squaring. So you take the modulus and square it, you will arrive at the same result. Problem 154 says that find the range of real numbers alpha for which the equation z plus alpha z minus 1 plus 2i is equal to 0 and z is equal to x plus iy has a solution. Also find the solution. So we are given z is equal to x plus iy. So we substitute this in the first equation. We get x plus iy plus alpha into square root of x minus 1 whole square plus y square plus 2i is equal to 0. So we equate real and imaginary parts. We get y plus 2 is equal to 0. That is y is equal to minus 2. And x plus alpha into square root of x minus 1 whole square plus y square is equal to 0. So we substitute y is equal to minus 2 into this equation. We will get alpha into x square minus 2x plus 5 is equal to minus x. We square both sides and bring everything on one side. We get alpha square minus 1 x square minus 2 alpha square x plus 5 alpha square is equal to 0. Now since x is real, the discriminant of this would be greater than 0. That is 4 alpha to the power 4 minus 20 alpha square into alpha square minus 1 greater than equal to 0. So we cancel out alpha square. That is, we take common and we remove it. We get 4 alpha square rather. We get alpha square minus 5 alpha square plus 5 greater than equal to 0. That means alpha will lie between minus square root of 5 by 2 to plus square root of 5 by 2. Problem 155 says that for every real number a greater than equal to 0, find the complex number satisfying the equation 2 mod z minus 4az plus 1 plus ia is equal to 0. So we let z is equal to x plus iy. So we get the equation as 2 into square root of x square plus y square minus 4ax plus iy plus 1 plus ia is equal to 0. Now we equate real and imaginary parts. We get left for real part 2 into square root of x square plus y square minus 4x plus 1 is equal to 0. And for imaginary part we have minus 4ay plus a is equal to 0. That is y is equal to 1 by 4. Now we take this value and we substitute in the real part, that is 2 into square root of x square plus 1 by 16 minus 4x plus 1 is equal to 0. Now it is a simple matter of simplifying this. We finally arrive at the result as x is equal to minus a by 1 minus 4a square plus minus 1 by 4 square root of 4a square plus 3 by 1 minus 4a square. Problem 156 says that show that x square plus y square to the power 5 is equal to x power 5 minus 10x cube y square plus 5x to the power 5xy to the power 4 plus 5x4y minus 10x square y cube plus y to the power 5 whole square. So we take x plus iy to the power 5. We get this as x to the power 5 minus 10x cube y square plus 5x y to the power 4 plus I into 5x to the power 4y minus 10x square y cube plus y to the power 5. Now this is a complex number equation, so we take modulus and square, we arrive at the desired result. The other way to do would be you write the expansion of x minus iy to the power 5, which would be this minus I into this. So once you do that, you multiply both x plus iy to the power 5 with x minus iy to the power 5, you will arrive at the same result. Problem 157 says that express x square plus a square into x square plus b square into x square plus c square as sum of two squares. So we just multiply this whole thing, we arrive at the result x cube minus abx minus acx minus bcx plus I into cx square minus ab plus ax square plus bx square. So we take the modulus and we square it, we get this result. The other way to do would be you compute x minus ia, x minus ib, x minus ic also, and then you multiply them, you will arrive at the same result. So there are two ways to solve these two problems, that is 156 and 157. Problem 158 says that if 1 plus x to the power n is equal to a0 plus a1x plus a2x up to an xn, prove that 2 to the power n is equal to a0 minus a2 plus a4 minus so on up whole square plus a1 minus a3 plus a5 minus so on whole square. So we are given that 1 plus x to the power n is equal to this expansion, so we substitute x is equal to y and we get the result as a0 plus ia1 minus a2 minus ia3 plus a4 and so on. So we split that into two parts, a0 minus a2 plus a4 minus so on plus I into a1 minus a3 plus a5 minus and so on, and then we again take the modulus and square, we arrive at the desired result. Similarly, what you can do is you can compute 1 minus I to the power n and then you multiply, so you will arrive at the same result. Problem 159 says that dividing fz by z minus I, we get I as remainder, and if you divide by z plus I, we get 1 plus I as remainder. Find the remainder upon division of fz by z square plus 1. So we can write fz is equal to mz minus I plus I, and fz is equal to mz plus I into 1 plus, plus 1 plus I, where m and n would be quotients on division. So since this is divisible, in this case we substitute z is equal to I, we get this term as 0, so fi would be I. And in this we substitute z is equal to minus I, so we get f minus I is equal to 1 plus I. Now we let gz be the quotient and az plus b the remainder upon division by z square plus 1. So we can write that fz is equal to gz into z square plus 1 plus az plus b. Now we substitute z is equal to I and minus I. So if you, in both the cases z square plus 1 will be 0. That is, this whole term will become 0. So I will be equal to ai plus b and 1 plus I would be equal to ai minus ai plus b. So we have two equations, two unknowns. We solve it to get values of a and b. Problem 160 says that if mod of z less than equal to 1, mod of w less than equal to 1, show that mod of z minus w square is less than equal to mod of z minus mod of w whole square plus argument of z minus argument of w whole square. So we take z is equal to r1 e to power I theta 1 and w is equal to r2 e to power I theta 2. So since mod of z less than equal to 1 and mod of w less than equal to 1, r1 and r2 both will be less than equal to 1. Now we compute mod of z minus w whole square. We get this one as, you can see the equations. This is the base equation, and then from this we arrive at r1 plus r2 whole, r1 square plus r2 square minus 2r1 r2 cos theta 1 minus theta 2. We add and subtract 2r1 r2, it becomes r1 minus r2 whole square plus 2r1 r2 minus 2r1, this should be r1 r1 r2 cos theta 1 minus cos theta 2. Now 1 minus cos theta is equal to 2 cos square theta, 2 sin square theta by 2. So this becomes 4r1 r2 sin theta 1 minus theta 2 by 2 whole square. Now we know that sin theta is less than equal to theta, so this whole thing becomes theta 1 minus theta 2 whole square, and this is less than equal to 1. So this is sorry, this is less than equal to theta, so this will be less than equal to r1 minus r2 whole square plus theta 1 minus theta 2 whole square. And thus we can say that mod of z minus w whole square is equal to mod of z minus mod of w whole square plus arg of z minus arg of w whole square. So with this, we come to the end of 16th set of problems on complex numbers. In the next set, we will solve next 10 problems. If you have found the video useful and informative, please subscribe to the channel and like the video. You might also want to press the notification bell icon. So if you have a comment or suggestion, or you want to say something to me, please make use of the comment box. I'll see you in the next video. Enjoy.